right, so welcome to Math 140 Calculus 2. So this is part 2 of the lecture on the German tank problem. And again, the purpose of these lectures is to show you what comes next year. What can you do after Math 140? What you need to be able to have real-world applications. And what's great is you will already have enough skills after this class to do more. And of course, the more math, the more stats you take, as well as other departments. I hear they do exist. You'll be able to do even more. But for many things in the world, you don't have to get the best answer. You just have to do better than is already being done. And so there's a lot of opportunities. And so this is also a chance to review some of the material we've seen in the semester. All right, so I want to talk a little bit about regression. So we've done this before. I'm going to submit someone else to the Zoom room. So we've done this before. So we talked about trying to find the best fit line. And one of the things you have to realize is, depending on what your definition of best is, you can come up with different answers as to what is the best fit line. So for example, imagine you want to buy a house. What do you think is the best feature of the house? Thoughts? Square footage. And there's a funny movie, War of the Roses, where a married couple gets divorced and neither one wants to give up the house. And so they split the house in half. And the lawyer's looking at the husband. You're crazy. No. I got more square feet than she did. You're crazy. You can't live it. So one is square footage. What else might you care about for a house? Number of rooms. So, you might have some rooms that are not that useful. So when we moved into our house, we had this great big room on the second floor, which was just too big. And so we actually put in some walls and split it into a bedroom, a laundry room, and what I now call a good room. What else might you care about? When you're older and you have kids, you'll care about this. The school district. What school district are you in? And so a lot of people are willing to sacrifice size of house for the quality of the school district. You might also care about how far is it to work? How much commuting time will you have? And so different people will have different opinions on what is the best. So when you're trying to decide how much is the house worth, it's worth different amounts to different people. So we talked about these different metrics. Sometimes you can clearly say this metric is stupid. The first metric is stupid. There's no nice way around it. There's no way to justify it. Yes, it's easy to work with, but negative errors can cancel with positive errors. The second and the third are both defensible, absolute value versus squares. I personally prefer the absolute value, but it's not tractable. You have to do computations, numerical routines to try to find the optimal answer. Whereas if we use the third and using squares, we can just write down in closed form using calculus and linear algebra what the best solution is. And so that is extremely valuable. You can then see how the best fit changes as you vary some of your parameters. All right, so we talked about how that allows calculus. And then going into what you'll see in multivariable calculus, when you have functions of several variables, you have the option of taking derivatives with respect to some of the variables, not others. And we saw in calculus that a candidate for maximum or minimum is either at the endpoint or where the derivative is 0. So in several variables, it's not surprising that what happens is you need the partial derivatives to both be 0. And so this gets you a system of equations, 2 equations, 2 unknowns, and then you can just go through and use linear algebra to solve it. So I'm not going to go through all the algebra because you've seen it before, but the slides are here. All right, we talked about how many nonlinear relationships become linear after applying a logarithm. And it's really worth driving home this point. If there's just one thing that I can have you learn when you finish the class with me, I'm a little bit upset. I'd like at least 3 or 4 things. But on any short list is whenever you see a product, think logarithms. And the reason is just we have experience dealing with sums. It's what we're used to. And so if we take a logarithm, we can convert a lot of relationships that are nonlinear initially to linear. So if y equals bx to the a, then when we take logarithms, we find that the log of y is linearly related to the log of x. And now all of a sudden these techniques apply. And of course, we could do things that are functions of more variables and more complicated relations. All that matters is that it's in a nice form in terms of the unknown parameters, the a's, the b's, and so on. Okay. So we talked about Kepler's third law. had a homework problem on this where the square of the period is proportional to the cube of the semi-major axis. And this was discovered numerically. This was discovered by looking at the data. It is a lot easier to make these discoveries now, where you can just have the computer do reams and reams of calculations. In the very first episode of Star Trek Deep Space Nine, they're trying to discover something. And so they tell the computer, investigate the last 10,000 years of all incidents of the following block. Working will take 6 hours. Okay, let's go to the holodeck and play. And you just program the computer, and the computer just does the number crunching. And the sheer number of comparisons that it can do is remarkable and can pick up things. Machine learning is an incredibly growing field right now. Computers have learned how to solve a Rubik's Cube just by taking a cube and randomly turning it and looking to see what happens. Absolutely amazing what you can do with the ability to process massive amounts of data. And so, this is the same as, if we take the square roots, t is proportional to the length to the 1.5. If we looked at the data, we did all this before. We see we chose units to make it really nice so that the constant would be 1. You always have some freedom in terms of choosing units. And you get one of the most beautiful straight lines you'll ever see. I mean, this is a phenomenal fit. And this just indicates the power. And again, if you didn't know that the relationship was the period squared is proportional to the length cubed, if you were to do this log-log plot, it would be yelling at you, slope of 1.5. So you have the ability to gather massive amounts of data and sift for patterns. And the more you can do this, the more likely you are to find something. It doesn't matter if 99% of the time you find nothing. If every now and then you find a relationship that no one has seen before, you can make a real contribution. And this is why I always encourage students, learn how to program, learn how to cull data from the web. I actually just passed on some opportunity to some Williams students of mine earlier today. I have some colleagues who are looking for somebody who can cull for a interesting project. I think we talked about the Boston Bridge and the Smoot, so I'm not going to go through Smoot again. I'm not sure if we did the birthday problem last time. Okay, we did the birthday problem. Excellent. So I will skip the birthday problem. So now let's go to statistics in the German tank problem. So just to remind it, because it's been 2 full days, the situation is the Germans label their tanks 1, 2, 3, all the way up to M. And you observe tanks S1, S2, all the way up to SK. So you observe K tanks with K serial numbers. And the largest serial number you observe is M. And you're trying to estimate what is the number of tanks as a function of M and K. And so we know there has to be at least M tanks. And so again, what I'm going to do today is I'm going to show you a lot of bad things, a lot of things that just don't work. One of the things that often happens when you're reading a math textbook or a physics book or a chemistry book, wow, it's amazing. Every argument always works perfectly from the start to the finish. There's no wasted steps. This is reverse engineering. Now that you know where you want to end up, you throw away all the false starts. A lot of times you learn more from false attempts. Anybody ever see the movie Chitty Chitty Bang Bang? Throw the roses of success. For every mistake you make, be grateful. That's a mistake you'll never make again. They did an interesting shortened version of that in the school play this year, which was a lot of fun to watch. And one of my favorite songs, there is value for making mistakes. There's value for just trying something and seeing. Well, I know there has to be at least M tanks. So let me choose some number N. I'll randomly choose K tanks from 1 to N, and I'll record the largest. And I'll plot the best fit line of N minus M as a function of M over K. Because I know there has to be at least M tanks. So maybe I should somehow take that into account. When you look at this, does this look at all like a good line? It looks terrible. I'm mixing up a lot of different things. And you're plotting N minus M, that's not a really good thing to do. N is fixing N beforehand, M is what's chosen. I'm really mixing up my axes. So even though I know that there's this boost from M, it's not necessarily a good idea to incorporate that. Okay. If you see a straight line looking at that, other than the blue line I'm physically forced to put in, you have amazing statistical intuition. Okay. I'm not going to go into too much detail on this, but this is plotting the log of N against the log of M and 1 over K. And if you look at this, this is actually looking like a pretty good plane. Just saying that there is a pretty good linear relationship in terms of what's going on. Now, if you remember, the formula was n is equal to m times 1 plus 1 over k minus 1. Can we all agree the minus 1 doesn't matter? This is Elon Musk finding out that Twitter asked for $1 extra. All right, fine, it's not going to stop the deal. Other things may stop the deal, but $1 extra is not going to make a difference. What really matters is it's m times 1 plus 1 over k. So if we take the log, we get the log of m, and then we get the log of 1 plus 1 over k. We can Taylor expand the log of 1 plus 1 over k. So remember, we showed the log of 1 plus x is x minus x squared over 2 plus x cubed over 3, and so on and so on and so on. So if k is large, 1 over k is small, which means that log of 1 plus 1 over k is approximately 1 over k. The next term would be of size 1 over k squared. And so this suggests that if our theory is correct, the log of n should be pretty well fit in terms of the log of m and the log of 1 over k. And we are seeing a plane like that. Okay, so what I want to do now is I want to talk about implementation issues. If we try to actually do this, what happens? And again, I want you to be thinking about what kind of sanity checks can we do on the data before we start doing the calculations. So if I'm doing probabilities, I'm trying to calculate, let's say the probability the Red Sox win the World Series. What can you tell me about that probability? You don't need any baseball knowledge. You should be able to give me some upper bound and some lower bound. It's between 0 and 1. No matter how bad you are not going to have a negative probability of winning the World Series if you're a baseball team. In fact, even if you're a football team, you will not have a negative probability of winning the World Series. And no matter how good you are, you're not going to have a probability greater than 100%. So we know it's immediately between 0 and 1. So if you see something that's greater than 1, you know there's got to be a mistake somewhere. And I was once looking at something that somebody outside of math was doing, going, your probability is sum to 2. I'm pretty sure there's a mistake somewhere in your argument that, and it turns out that they were counting too many things. So you always want to be able to ask, is this reasonable? Let's say I win 80% of my games and I play a 1-game series, winner takes all. What's the probability that I win? So I win 80% of the time, I play 1 game, winner takes all. What's the probability I win? 80%, right? What if we played 3 games, winner takes, you have to win 2 out of 3. Do you think my chance is greater or less than 80%? Well, which is it? So let's go to an extreme case. Imagine you play 1,000,000 games and you have to just win, so let's say 1,000,001, it should be an odd number, 1,000,001 games. So you just have to win more games than you lose. If you win 80% of the time, do you think you're more likely or less likely? More likely. Do you think it's more or less likely than 80%? If you win 80% of the games, how many games do you expect to win if you play 1,000,001 games? Roughly 800,000. You win the series if you win 500,001. Do you think it's very, very likely? Likely? Maybe 50%? How likely do you think it is if you play 1,000,001 games that you win at least 500,001? I'm sorry? Do you mean very close to 1, very close to 80%, close to 90%? What do you think? So let's go to an even more extreme. Let's say you play 1,000,000,001 games. You would expect to win 800 million. You only have to win, 500 million. You're playing so many, you're winning with such a greater frequency. Do you think it's going to be extremely close to 100% or close to 90% or close to 80%? As we keep playing more and more games, the probability that you just win more than half, it should get close to 1. This is what's looking at extreme cases. In one game, I'm going to lose 20% of the time. But if I play 3 games, in order for me not to win, I have to lose 2 out of 3 games. I could lose all 3 games, which would be 0.2 cubed, or I could lose 2 out of 3. There's 2 ways to choose which games I lose. So it'd be 0.2 times 0.2 times 0.8. And so when you add that all up, it's going to be, the probability that you lose is going to be less than 20%. You're going to win more than 80% of the time. And as you keep going to greater and greater extremes, you're going to have a higher and higher chance of winning the series. Because the more games you play, the more powerful your advantage is. You can afford to have one day where you just have a bad day. But most of the time, that's not going to happen. So in longer series, the better team has a much greater chance of winning than in shorter series. This is why you'll see more upsets in football than you will in a sport like basketball. You always want to be able to ask these extreme cases and try to say, is this answer reasonable? And so just trying to get a sense of, do I think my chance of winning a series is increasing with the increasing number of games? Yes. All right. So let's start looking at the German tank problem. So again, theory says it should be 1 plus 1 over k times m minus 1. So I'm going to plot n versus the maximum observed tank, m. So m is on the horizontal axis, n is on the vertical. I did, I think 10,000 trials and going from maybe like 1,000 to 10,000. So k equals 1, and my best fit line is n equals 0.784m plus 2875. When you look at this best fit formula, could this best fit formula work for all m? Or is there something about this formula that seems a little fishy to you? So I'm claiming that the best fit line is 0.784m plus 2875. Now, if you look at the data definitely does not look like a line. It looks trapezoidal. Maybe the line is somewhat in the middle, and maybe it's kind of balancing, for maybe there's more points in the right part than the left part. But could this formula possibly be true for all values of m? Why not? Okay, so one thing is I could try to extrapolate down to small values of m. But what about large values of m? As m goes to infinity, could this be reasonable for the best fit n? So again, try to think, what's a test I could do? This is predicting an n. Give me a large value of m, a nice easy number to work with. 100,000. Let's just do it a million. It's a little bit easier. So let's do m is a million. So what would be the prediction if m is a million? Approximately what? Around 800,000. So if m is a million, so you observe a tank with serial number million, you're predicting 800,000. What's the issue? So you should have seen that immediately. And again, this is why I really want to take the time. I'm not planning on doing much material today. This is just deep life advice on how to look at equations. What is the simplest smell test I can do? Well, n has to be greater than m, or at the very least, it has to equal m. Now I've got the plus 2875, so for small values of m, it's okay that this constant is less than 1. But there's no way that this constant can work in general. I think at the start of the year, we might have talked about special relativity and adding speeds. Did we do that? Or was that just in 150? Okay, so if you look at, say, a train traveling at 100 miles per hour, and I think it's a requirement that all examples in special relativity involve trains, because that's what was the fast method of transportation when Einstein was developing this. So if you have a train traveling at 100 miles per hour, and you're on that train and you run in the same direction as the train at 10 miles an hour, somebody on the ground who's stationary, it looks like you're traveling at 110 miles per hour, but you're not. Speed is not additive. Nothing, according to current theory, goes faster than the speed of light. And so the speed is not 110, it's a little bit less. It's less by so little that for the most part, we can't detect it without really good sensitive equipment. So you've got to be careful about trying to glean too much information. And you might say, well, this line was devised in this region. It doesn't work for larger values. Okay, but I really want something that should work for all values of m. It shouldn't be dependent on the fact that I'm going in this range. This is giving us some idea that there's issues with this best fit line. And I know that that constant should be at least 1. Our theory is it should be 2m minus 1. All right, so let's try k equals 2. Do you think that this line could be good for all values? So this is now n equals 0.964m plus 1424. Yeah, it's still under 1. Your theory says it should be 1.5. Even if I don't know the theoretical result, I know it has to be at least 1 times m. So I know this is out. If I now do 5, and notice that the data is getting a little bit tighter. So it's actually looking better. When I take k equals 5, I now get 1.037 versus, oh, it doesn't show over there. That's annoying. All right, so my best fit line is 1.037m. The best fit theory, the theory is 1.2m. Right, 1.037m is at least greater than 1. So even though it's not as high as the 1.2, it's at least above 1, so it's now reasonable. And I do apologize that Zoom is not showing everything clearly, but you can at least see that has to be a 1. So, maybe if I start taking even larger values of k, I will finally get something that is reasonable. The reason this is not working out well is I'm having, when I do my method of least squares, the x-axis is supposed to be your independent variable, and the y-axis is supposed to be what you measure. Here, I'm putting on the x-axis what I measure, the maximum observed tank, and I'm putting on the y-axis what I'm choosing, my n. I flipped them, and that's what's causing the trouble. Just the way I think about things, that's how I should do it. But so let's flip it. So let's put the number of tanks on the horizontal axis and the maximum observed on the vertical. And again, we do now m equals 1. I'm sorry, k equals 1. We have the trapezoid again. The theory now is instead of having n is m times 1 plus 1 over k, it's now m is equal to k plus 1 over kn plus a small constant. And so theory says it should be 0.5n plus 0.5. We observe a best fit line of m equals 0.496n plus 10.5. That's impressive. When you look at it, the fit doesn't look that great. There's a lot of variation going on. But in terms of just numerically, coming up with the right line, 0.496 versus 0.500, I'm quite happy with an error that small with real world problems. I'm a little bit off in the intercept. Okay, but if I'm talking about thousands of tanks, being off by 10 out of 1,000, it's not a big deal. When I was talking about earlier, I think we talked about the Chapter 70 funds for the 3 schools in our district and trying to assign the money to them. No, I didn't do that in this. All right. I'll skip that comment. All right, so instead of doing k equals 1, we can do k equals 2. And now the theoretical line is 0.667n plus 0.667. The best fit line is 0.668n plus 9.25. So again, absolutely wonderful fit. If we go up to k equals 5, as before, it's getting tighter. Theory is a slope of 0.883. We're getting a slope of 0.828. Again, extremely reasonable. So what this is telling us is that if we just randomly choose a lot of n, choose, say, 5 tanks at random from 1 to n, 5 serial numbers, and in the old days, what you could do if you didn't have a computer, just put slips of paper in a ball, in a jar, and just reach in and pull it out. And just sample without replacement. and then you record the largest value of m. We could numerically do this experiment. And this will give us a slope. And then we can go into the field and say, well, okay, if you've observed this as your largest tank, and this is how many tanks you've observed, this is what we would predict. So this can be done with extremely primitive technology. Here's another way to try to make things a little bit better and to cut down on the variation. What we did for this one is for each value of n, I did 100 samples. I did 100 trials. And for each one of them, I then recorded the average value. And so that tightened things up a lot. That really compressed things. And if you look at this now, it really looks like a line. And now I'm actually getting a good fit, n equals 1.5 m minus 1 versus 1.496 m plus 171. Okay. So the last one I really want to talk about today is what if we didn't know that n was supposed to be m times 1 plus 1 over k? How could we try to figure this out? So what we can do is for each choice of k, so k is going to be my x-axis, the number I'm observing, I'm going to plot the best slope. I'm going to write n is equal to a times m plus b, where a is going to be a function of k. What can you tell me about a? So I'm writing n as am plus b. What must be true about a? It's greater than or equal to 1. If you look at the y-axis, what do you notice about the y-axis? It starts at 1. So a lot of people can play with charts to make you think that there are huge differences when they're not, depending on how you label things. Does it look like there's a large variation in the y values? I mean, it looks, you've got huge distance on the x-axis and you're a huge drop in the y, but you're dropping from 1.06 to about almost 1.00. You're dropping by a very small amount. And so, months ago when gas was released from the strategic reserve, if you just focus on what the price of gas was to within maybe plus or minus 10 cents, it looked like there was a huge drop from the gas being released. If you then zoomed out, you see proportionally very small. So you can play games like this all the time in terms of what you want people to look at. This is not things you should be doing. Just to make this absolutely clear, and anybody who stopped the video and quoted me on just that is not doing justice. You should not be manipulating people's perception by how you present the data. As a rule of thumb, what job requires you to be phenomenal at manipulating people's perceptions? Paul, not going to answer that one, but that's being recorded. So I think I can say yes to sales, to marketing in terms of, I heard an interesting joke and I will share that maybe after class when we have a technical malfunction. Magicians. Magicians are phenomenal at getting you to look at the wrong thing. And I think I might have talked about how 2 of my friends left college to help the amazing James Randi set up his institute. So I've heard him give talks and just absolutely amazing how he can get people to look at the wrong thing. So, he was speaking at Princeton, and when he was at the podium, he was very easy to hear, but as he moved further from the microphone, it was harder to hear what he was saying. Why do you think it was harder to hear what he was saying? As he moved further, as he got closer to the podium, it was easy to hear him again, but as he continued to walk like I'm doing now, it was harder. Why do you think it was easy to hear him when he was near the podium with the microphone? Distance from the microphone. The microphone was off. He had a microphone inside his collar, and he was controlling it with a device in his hand. But making you think, and again, he just said this is just one of many, we have many tricks we can do to get you to look at the wrong thing. So whenever you're looking at data, always ask, who is the source? What are they trying to get you to see? You be very careful, be very clear in what you state. Unfortunately, things can be taken out of context, so you've got to be very careful. Here, we're going from 1.00 to 1.06. There's really not that much dependence. So my question is, the A is the more important number than the B. The slope is what really matters. The intercept is not as valuable. When you look at this, does this look like any curve you know? Okay, what curve? Or can you give it to me algebraically? Y equals, any thoughts? 1 over, you could try maybe y equals 1 over x, but is your eyesight, your mathematical eyesight so great that you can see the difference between 1 over x, 1 over square root of x, 1 over x to the 3/2, 1 over x log, but roughly maybe something like 1 over x. But we know it's, as x gets large, what does this seem to converge to? 1. So maybe it's 1 plus 1 over x or something like that. And of course, we know theoretically it's 1 plus 1 over k times n. So we actually do know it's a hyperbola. It's a special hyperbola, just shifted a little bit. But imagine we don't know that and we just see this data. So we just do the experiment for many different values of k, and we record the best fit value of the slope for each k. And now I want to see, can I prove that this is 1 plus 1 over k? All right, well, let's look at things. So what I'm going to do is I'm going to do a log-log plot. I'm going to take the log of the number of observations, because that was the x-axis, and I'm going to take the log of the slope. And so when I do that, I could plot the log of A, but I know A has to be 1 plus something, right? I'm not going to have fewer tanks than the highest observed. So I'm going to plot A minus 1. That's the only common sense thing I'm allowing myself to do. So I plot the log of A minus 1 versus the log, which is the log essentially of the slope, against the log of k. And so the best fit line I get is the log of A minus 1 equals negative 0.999 log of k minus 0.007. It's a nice coincidence that you have the James Bond number arising here. All right, so do we all agree that 0.007 is essentially 0? So this means the log of A minus 1 is basically negative log k. All right, well, if the log of A minus 1 is negative log k is just the log of 1 over k. I just use the power rule. So the log of A minus 1 is the log of 1 over k. So A minus 1 is 1 over k. So A is 1 plus 1 over k. We were actually able to come up with a conjecture for what is the function of k in front of m, just by looking at the data. We didn't have to do any math tricks. Just by gathering the data and doing a log-log plot, we were able to sniff this out. And to me, this is just an absolutely wonderful example of what you can do with math and stats. We now have something to try to prove. We now have an idea that, oh, okay, it is a 1 plus 1 over k relationship. And then you go to your theorists and say, prove this now. And if you don't have theorists, what you say is, well, we're going to just operationalize this, and we're going to just say, we're going to work under the assumption that this is always true. We numerically observe this in a large regime. We're going to continue. Anybody ever read David Hume, philosopher? Just because the sun rose yesterday doesn't mean it's going to rise tomorrow. No, but all things being equal, I'm going to act under the assumption that it will rise tomorrow. And so, a lot of times you can observe these numerical relationships, and you might be willing to just say, I'll always try to see if I can confirm them or prove them, but I'm willing to just keep using this for a while. So I hope this gives you a sense of the power of what we're doing. Too often in classes, we present everything as these beautiful, completely elegant theories from start to finish, where everything just follows nicely, line to line to line to line to line. Here today we had some false starts, and we tried a couple things and it didn't work. And eventually we found, here's a good way to look at the data. Here's a few good ways to look at the data. And from this, we were able to make a conjecture from the data. And even if we can't prove it, it looks so good that we are quite comfortable extending this further. If you look at this as a straight line, for real world data, this is not bad. All right, so did I ever tell your class whatever happened to Mr. Smoot? Okay, so he had a couple of choices. He could have been kicking and screaming when they decided they wanted to use him as a unit of measurement, or he could have just rolled with the punches. He rolled with the punches, and you can't make this up. He became the chairman of the American National Standards Institute and the president of the International Organization for Standardization. And I'm just trying to imagine his job interview. Well, I don't like to brag or anything, but I am a unit of measurement. A huge part of life is being able to connect with people, is being able to have stories. The first winter study I ever taught was Introduction to Cryptography. And I encrypted the title. And I was contacted by Williams, or something like that. That's the title. You want that on students' transcripts? Absolutely. And several of my students told me that when they were having job interviews, people said, I've got to ask, what is this on your transcript over here? And all of a sudden, it was a conversational starter. It was an opportunity to talk about something that they wanted. So one of the great skills that you get from being at a liberal arts college is the ability to talk to diverse people for large amounts of time on almost anything. You should be able to talk on almost any subject for 15 minutes to an hour. After an hour, it's okay to be running into problems. I was being interviewed at a big financial firm in New York City years ago, and it turns out that the person who was interviewing me was a art history major from Williams. And this was actually the same year I applied for the job at Williams. And I really didn't want to leave academia, but I was willing to go for the job interview. And they told me that my lunch with this person is not part of the job interview. It's just a chance to relax and have questions answered. Oh, sure. And so the question is, can I, a cultural Philistine, talk about art history for lunch? Absolutely. If I had to talk to her for 3 hours, I'd be in trouble. I'm actually meeting one of my good friends who teaches in art history here in a few minutes. We've never fortunately had a 3-hour art history conversation, so I'm always fine with him for short periods of time. But I was one of the few people she remembered interviewing. And years later, when she had her own firm helping people find jobs, one of her clients was very high up in sports analytics in one of the major sports. And she connected me with him, and we got him to come to Williams, give a talk to my probability class, and mentor some of the students. You do not know what connections you will make. And this is why if you don't take a job, don't do things that will shoot yourself in the foot. Try to leave good experiences on all sides, because you may come back later and work with them, which has happened to me numerous times, both with jobs I've declined as well as people who've declined to come to Williams. So I absolutely love what this person ends up doing with his life, and just imagining the fun he must have had relating those stories. All right, so here's a list to some of the papers. I'm not sure if I've linked. No, I don't think I've linked the final paper that we've published on this, because that was written after all of this. And then I want to just quickly go through, just because things are being recorded, is just how you would set up the more general problem, to just see that it does get a little bit more involved as you go deeper. There is a reason why we have additional theoretical math courses. So we have N1 is the low, N2 is the high. The total number is N2 minus N1 plus 1. The observed smallest is M1, largest is M2. The spread is going to be M2 minus M1. And then we need to prove certain results. So we have this beautiful formula that we saw before. Summing L choose A from A to B is B plus 1 over A plus 1. So this is the formula we had before. And then we just start computing the spread. So the expected value of the spread is just S times the probability S equals S. And we use the result that I mentioned last time, that we have an explicit formula for that. And then we just substitute everything in. And then the goal is we just try to work with as many binomial things as possible. We use various identities. And we just do a bunch of algebra. And so we split things up into two sums. We handle the sums one at a time, and we keep working on them until we can get something nice. And you just do some algebra, you follow your nose. If something doesn't work, put it off to the side, try something else, and hope eventually you get to something that's nice. And then you work on the next piece, which is a little bit more involved. And then that next piece ends up having two other pieces you have to work with. And then we analyze those pieces, we get some nice things. And then eventually we put everything together. And then we do some more simplifications. And finally, we obtain a really nice formula. The expected value of the spread is just n plus 1, k minus 1 over k plus 1. And then we can unwind and get the best fit value for the expected value of n. So the algebra you could follow. You can follow it line by line by line. It is not challenging. It's much easier to follow proofs than it is to come up with them. And how do I think to do this algebraic step? A lot of it is pattern recognition. This is the baby crying. At this point, if you have to factor a polynomial and say, I give you a quadratic and it has integer roots, you should be able to look at it now and you can just see what it is. But when you were starting, it was probably very hard. Hopefully now, if you have to do some integrals, you can quickly look and say, oh, this is a partial fraction, damn. This is a U substitution. Thank God, I love U substitution. You should be able to just look at it and see what should you try. And then as soon as you know it's U substitution, now what do you have to figure out? What's the U? And it's like, oh, okay, there's a couple of different choices for the U. Let's see if this works. No, let's see if this works. No, let's see if this, good, this one works. And then some U substitutions are done so often that they have their own name. And we call these the special type of U substitution. We use a special type of functions. The trig substitutions, right? So the trig substitutions are just a special case of U substitution, but they occur so many times. You basically say, look, if you ever see something of the form 1 plus x squared or a plus x squared, something like that, use a tangent substitution. And so that's what a lot of this is like. Just the more times you do things, the easier it's going to get. All right, so this is a good place to stop recording.